In this video, we'll talk about matrix operations, which are addition and multiplication. Before we start, let me introduce a general m by n matrix. So in general, when we say an m by n matrix, sorry, that was meant to be an n, we mean that the matrix has m rows and n columns. Let's say that's the matrix A of size m by n. In general, I can represent it in this way. A, 1, 1, so the indices say that this A is in the first row and first column, then A, 1, 2, first row, second column, all the way to A, 1, n. So that's the nth column. Then in the second row, I will have A2, 1, A22 all the way to A2n. And then the last row will be AM1, AM2 all the way to AMN. So this is an m by n matrix, which we write in the lower right corner. The entries are A. Sometimes we also write this A in this way, Aij. So we refer to Aij as the entries of A, or rather Aij is the entry of A, which is in the ith row and jth column. So this is the entry of A in the ith row and jth column. All right. Now with this, let's talk about matrix addition. Matrix addition is very easy. It's exactly what we would expect it to be. It is term by term addition. The only condition then, in order for us to be able to add two matrices, is that they are of the same size. So this m by n is what we call the size of a matrix. So we have different matrices, 2 by 3, 2 by 2, 3 by 3. So far we've been working with square matrices, which were 2 by 2 or 3 by 3, but we'll change that going forward. So for matrix addition, we can add matrices provided they have the same size. If they're of different size, we cannot add them. And the addition is term by term, or component by component, as one would expect, just like a generalization of vectors, you could say. By the way, with this definition that we have for an A, it turns out that a column vector would be, say, of size m by 1. A row vector would be of size 1 by n. So we can refer to vectors as matrices as well. All right, let's look at an example. So this will be a matrix with 2 columns. So this is a 3 by 2 matrix. And we can add it to another matrix of the same size, 2, 4, 9, 2, 4, 9, for example. And what we do is we add things term by term. So for example, this number plus this number is 3, and then correspondingly. So then one next to it would be 2 plus 2, which is 4. Then 3 plus 4 is 7, 4 plus 4 is 8, 0 plus 9 is 9, 0 plus 9 is 9. So this is what we refer to as the sum. Similarly, just like what we had for vectors, if I multiply a matrix by a constant, by a scalar, it is just like with vectors. The multiplication is done term by term. So this would be 2, 6, 0, 4, 8, 0. So exactly what you would expect, nothing special here. We still have to respect how it works. All right, now multiplication is a little bit different. Before I define how to do matrix multiplication, which we almost have but not quite, we will do that in a moment, let me say something about when I can multiply. So let's say we have matrices A and B. Then the product AB is defined if A has n columns, for example, and B has n rows. So this is important. The first matrix must have n columns and the second must have n rows. Let's draw a picture of that. So here, this matrix would be m by n. So what that means is that each row vector here would have n components. Let's say the first matrix is of size m by n. We don't care how many rows it has, but each row has n components. Then the matrix B must have n rows, so this has to be the same, also n components. There can be multiple columns, so this matrix has to be n by, for example, k. M and k could be the same or they could be different, it is not important. Why would this be the requirement? Well, if you remember, let's think of the matrix here as multiplying just one column. You would want, if you did it row by column, you want the number of rows, the number of components in each row to match the number of components in each column so that you can actually carry out the dot product. And in fact, one way to define matrix multiplication is to define it through multiplication of a matrix by a column. So you compute this is a column, then you take the matrix times the second column, which gives you another column, then you take the matrix and a third column, which gives you another column, and you could get the matrix multiplication in that way. Now, we're actually going to define matrix multiplication in 4 ways. I'll write that. Matrix multiplication in 4 ways. It is possible to do it in 4 ways, and each way has something different to reveal. So the first way is the entry in row I and column J of the product AB is the dot product of row I of A and column J of B. So it is a dot product. Let me represent A through its rows. So let me say here row 1, row 2, row I, and so on, times, and now I will represent B through its columns. So C1 would be the first column of B, C2 would be the second column of B, then CJ would be the jth column of B, and so on. Don't know how many there are. It's like K. Then the product would be R1 dotted with C1. That would be the first component. R1 dotted with C2, and so on. And here we would have R2 dotted with C1, and so on. And in fact, let me just say here, we would have Ri dotted with Cj. So this row and that column would give us the component in the product that comes from the ith row and the jth column. So I could say the matrix AB, the component ij of the matrix AB is Ri dotted with Cj. You can use this method of multiplication if you have two matrices with all the numbers inside and you're just doing a calculation, which will rarely be what we will do in this class. This is what you would teach a computer to use if you wanted to, if you just wanted an algorithm. But in fact, we will rarely use this method of multiplication. All right, now let's talk about the second method of multiplication, and then we'll look at some examples. So the second way is matrix A times every column of B. So if I represent B with columns B1 all the way to say BP, there are P of them, then I can look at the matrix AB as AB1, that would be the first column, up to ABP. This is actually what we have done, or sort of the most natural way for us to extend what we have been doing so far. If we look at an example, let's say the matrix 1, 2, 0, 1 times this other matrix, and I'm going to change colors here just so you see. So let's say 1, negative 1, 2, 3, and then maybe negative 1, 1. So the matrix B has 3 columns, which is fine. What matters is that the number of components in the rows of A matches the number of components in the columns of A. So then what we get in the product is, if you take this matrix and multiply it only by that vector, what do you get? So you can compute that using dot products, you can compute it using linear combinations. It's up to you. Let's do with linear combinations, just so we can see what it is. So this is 1 times the first column minus 1 times the second column. And this gives us 1 minus 2 is negative 1, 1 minus 1 is 0. So this will go in the first column of the product AB. Now, if I go for the second column, I can compute it. So we have 1, 0, 2, 1 times the column 2, 3. Let's say we do this with dot products. So the dot product of the first row with the column matrix would be 1 times 2 plus 2 times 3. So we have 2 plus 6 is 8. And then the second row times the column vector would just give us 3. So that goes in the second column. So this is here, 8, 3. And then the last one, we have 1, 0, 2, 1 times negative 1, 1. This is negative, well, let me just use dot products here. It's just the least writing. So this is negative 1 plus 2, that's a 1, and then the second component is a 1, and that goes right here. So that's the second way to compute the product. It literally extends what we have seen so far. You just do matrix times a column, which we've done quite a few times. Now, what about the third way? So the third way says every row of A times the matrix B. We haven't done this type of multiplication because we haven't worked with rows, but it isn't very different. So let me show you a picture. If I take a row I of A and multiply it by some matrix, let's use numbers. 1, 4, 7, 2, 5, 8, 3, 6, 9. So this would be the matrix B. Then when I take that product, what I will get is the ith row of the product AB. In fact, maybe I should have just used the same example as before. Let's do that. So we have the same matrix, 1, 2, 0, 1, times the matrix 1, negative 1, 2, 3, 8, 3. Now what we're interested in is the rows of A. So maybe I should change the colors there. And just so we can see better. So 1, 2, and then 0, 1, because the rows are what matters here, equals. So now I want the first row times the matrix. So let me write that on the side. I have 1, 2 times this matrix, 1, negative 1, 2, 3, 8, 3. Now, of course, how do I carry this out? Well, I could just use dot product. So, or the previous method. This row times this column. So you can, this row is, think of it as a matrix, and we can use the previous method. So that row by that column just gives us a number, and we are expecting that the result will look exactly like this, a row vector with two components. So when we take the dot product of the row with the first column of B, what we get is 1 minus 2, which is negative 1. Then when we take it with the second column, we get 2 plus 6, which is an 8. And when we take it with the third column, we get 8 plus 6. Did I copy that? Oh, I copied that wrong. That should not be, that's not the same matrix. That's not 8, 3, that's negative 1, 1. There we go. So when we do it with negative 1, 1, we get negative 1 plus 2, which is a 1. So we'll write that as a first row here. And then for the second row, we have zero, 1 times the matrix 1, negative 1, 2, 3, negative 1, 1. And when we carry out that multiplication, we're going to have a row vector with 3 components. So 0, 1 times 1, negative 1 gives us negative 1. Then the row 0, 1 times column 2, 3. So you're taking dot products of the row with the column. So that is this 0 times the 2 and 1 times 3. So that just gives us 3. And then we do that with the last column. 0 times negative 1 is 0, plus 1 times 1 is 1. We get this row. We write it as a second row in our answer. Negative 1, 3, 1. And we are done with the multiplication. And if you compare, oops, we have a mistake. Why do we have a mistake? How did I get the 0 there? Okay, so obviously this is wrong because I have 1 times 1 here. So let's fix it. That's how you catch mistakes, when you do it with more than one method. So here we have -1. And here we have -1. And now they match. -1, -1, 8, 3, 1, 1, done in 2 different ways. Now, the last way, the fourth way to do matrix multiplication. Okay, let me change colors here. The fourth way is columns multiply rows. This is an interesting method. Let me show you with a picture. So let's say here we have column 1, or I guess I should be consistent. So if I represent the first matrix through its columns, and let's say it has only 3 columns, and I represent the matrix B through its rows, then here what we get is column 1 times row 1, but this is not a dot product. This is a matrix times a matrix type of multiplication, plus column 2, row 2, plus column 3, row 3. Let's go back to our example. So just the same example that we did above for the where they don't have 3 columns, but it's not important. So we have the matrix 1, 2, 0, 1. I guess I will use colors again just to represent things. 1 and 1, 2, 0, 1. That's how that matrix looked. The other matrix I'm going to represent through its rows. I'll use the same color, it's just too much to change. 1, 2, -1. And then -1, 3, 1. Now, what this procedure is saying is take the first column, so we have the column 1, 0, times the first row, 1, 2, -1, plus the second column times the second row. And this is, again, matrix multiplication. So what we're going to get here are 2 matrices of the proper size. What would the proper size be? Well, you see here the answers, they're the same size as B, or rather 2 by 3 matrices, for example, right over here. So we are expecting to get that, and that's exactly what will happen. If you look at the first column vector, the size of it is 2 by 1. The row vector is of size 1 by 3. That tells us that the answer will be of size 2 by 3. And the same is true for the second part. So we know what the answer will be from the sizes of the first matrix. Did I write that at the very beginning? Where I said that we can multiply. So here I should have added that the answer will be a matrix of size m by k. So n allow us to multiply 2 matrices, and then the outer indices put together tell us the size of the product. So this would be A times B. All right. So how to carry this multiplication? Well, use any method from before. You see this number is the first row of the vector, and this number is the first column. So you could do row times column, row times column, row times column, and you will obtain everything. So let's go back. First row times first column is literally 1 times 1. Then first row times second column is 1 times 2, which is a 2. Then first row times third column is 1 times -1, that's just -1. In other words, it's 1 times that row vector, and now we have 0 times that row vector, so we just get zeros over here. Plus, now the first row in the answer here is 2 times this row. So I can just directly write -2, 6, 2. And then the second row comes from 1 times this row. So I will just write -1, 3, 1. These two matrices are of the same size, so I can add them up, and I add them up term by term. 1 plus -2 is -1, 2 plus 6 is 8, -1 plus 2 is 1, 0 plus -1 is -1, 0 plus 3 is 3, 0 plus 1 is 1. Let's compare. So the first row is -1, 8, 1. If you compare the two matrices, you see that they're exactly the same. All right, that's enough for this video.